Yeah, hello, good morning everyone. Thank you very much for this introduction. I'm really excited to be here and to talk about where I see the future of scientific research combined with AI. I have to say, as Olga already mentioned, I recently moved back to academia. I'm building my own group, and one thing there were 2 points I always wanted to do when I give a talk like that, like really do good credit assignment and not just babble about my own work. The first is really easy because I have very bright students. The second is a bit hard because if you move from industry to academia, you suddenly have all the freedom where you can do whatever you like to do and which gets you excited. So it's very hard to not talk about these things. So I won't be able to fully contain myself. So I will start the talk with a picture I did like a couple of days ago. So as Olga said, I did my PhD at CERN. And it was the first time in, I think, 6 or 7 years that I visited this amazing place. And it's quite remarkable because things didn't change a lot in high energy physics. There's even my sign of the name on my old office still. And this is the plot of the Higgs boson discovery in 2012, which actually got me excited to go into high energy physics. But the progress there is really slow, although when you discover something, it's for eternity. This is very different to AI, because in AI, and funnily, the ImageNet revolution in 2012 really coincides with the Higgs boson discovery. It's basically was the same month, but since then the progress in AI is unmatched, I would say, and finally a new revolution comes every 5 years. So 2012 ImageNet, 2017 transformers, 2022 large language models or the ChatGPT model architectures, and yeah, the next one probably 2027. And these large language models and generative AI is the driving force. We all know that. I mean, there are new startups, Mistral, Claude, there's OpenAI with the GPT models, and now recently we get these amazing videos which really seem surreal if you compare them to the progress which was made to the videos, to quality of videos like just 1 year ago. I'm sure everyone knows this Will Smith movies, and if you do this comparison, it's just mind-blowing. And it seems really to be the lesson to fully kick in. It's the data and it's the model, and we can plot these scaling curves, and they justify all these resources which are put in. So there's a lot of discussion on where this is going, but nevertheless, this is the driving force of AI at the moment, and this is the way that the field is currently moving. And so I want to begin this talk with actually asking what's the question of what's the language of science, because apparently language is the most important part in driving the progress of AI. So if we want to bring AI and science together, we have to talk about the language of science. And this is clearly differential equations in all its form, ordinary, partial, or stochastic. And these differential equations, they go through many scales, both in time and in space. We can start on the very left, where I did my PhD in particle physics, going over quantum chemistry. Each of these fields are described by Schrödinger equations, relativistic or non-relativistic Schrödinger equations. Then we come to classical chemistry, where we have force fields, and we use Large dynamics to relax particle movements within these force fields. And then we come into this middle regime of fluid dynamics, which is basically the backbone of engineering in all kind of simulations, be it like smooth particle hydrodynamics, discrete element methods, or grid-based methods. And this goes to weather forecasting, and all of this area is driven by Navier-Stokes equations. And then finally we go to astrophysics and enter the realm of Einstein field equations, general relativity. So orders of magnitude and different kinds of equation, but this is really how we describe what is going on in science and engineering. And the way we model that is by writing these equations down. Usually they are time dependent because we model things that progress in time, that evolve in time. So we have some derivative of the time on the left. So that's the update of our system, and then we have all these partial derivative with respect to space, which can be convective terms, diffusion terms, and mixing terms, and so ever. And then we have a condition, what's the initial condition of our system, and the boundary condition. So what's the start in time, and what's the end in space, so to say. Very, very roughly speaking, there are two main simulation methods which we have. One is the Eulerian, and the other one is the Lagrangian method. Eulerian means that you have a fixed grid. This can be on a manifold, this can be just on a plane sphere, this can be regular, this can be non-regular, but this grid basically stays, and you calculate your derivatives on this grid and update them in time. The Lagrangian point of view is you follow particles through space, and by doing that, basically you track these particles, you track their interaction. Eulerian and Lagrangian have different properties, they model different phenomena, and therefore, they can describe different problems, the one better, the other can describe other problems better. So these are in a very short notice, these are the fundamental concepts I will talk when talking about PDEs. And now we basically go a step further and look into machine learning approaches. And there is, in my rough overview, two different directions. The one is physics-informed neural networks, and the second one is operator learning. Physics-informed neural networks is really using all the information of the equations to build neural networks out of them, ideally even without using any data. So all the information comes from the PDEs. We will talk about that later in this talk. And the second one is operator learning, where you map the state of the system, like a weather state, to future states in time. There has been tremendous success in weather modeling, which we recently witnessed, and it's in my opinion, it's truly remarkable, because this is weather modeling is such an interesting phenomenon, because we can just guess what the weather is. We can just write down equations which we think are true, but nobody really knows how to write down the equations of the weather, how to really model weather at all scales. The only thing which we really have are the data. So deep learning has this tremendous advantage, because it can understand the patterns from the data, whereas humans have to basically write down and guess what these equations are. So this is one of the fields where it's very clear that AI has a tremendous impact, which it is already having at the moment. So we will start with operator learning, and there the name of the game is basically you suddenly have continuous fields, which are called finite functional data. So you, instead of having like an MNIST ImageNet image, you suddenly have to model a continuous field, like a continuous function over space and time. And this has started a new learning paradigm, because suddenly, as I already said, you have a function of time, like a trajectory, and a function of space, like a continuous signal. So what is happening that there is this paradigm which started like 4 or 5 years ago, that instead of we learn this mapping between discretizations, as we usually do in machine learning, where we learn a mapping between different words, so some words in and new word out, a mapping between images, we suddenly learn a mapping between functions, which is called operator learning, and this allows us to learn the underlying dynamics of such systems, as it's very true in, for example, weather modeling, where we have these continuous signals over space and time. So when we, as I already said, we have these two paradigms, and in operator learning we heavily rely on data. So the first question you ask is definitely, where is this data coming from? Because it's not like language, where we can just get all the data from the internet and get all the images from the internet. We just have to get this data from somewhere. And I want to start with a work which basically changed the way I was thinking. So back when I was at Microsoft, I spent some time in Seattle with great collaborators, and we built this model. It was called Climax, and the idea was to build a foundation model for weather and climate. But for me, the more interesting idea was more philosophically. So we ask ourselves the question, how do we get like huge amounts of data? How we get human knowledge into all these into our models. And there, the idea was that there is like 15 years of climate simulations. Basically, there are, I don't know, 50 different weather offices around the world, and they do all their climate simulations for very different scenarios. And they all store this data. So it's like a tremendous chunk of data which is stored, which is lying around. And all this data basically has the human knowledge about what they think weather or climate is going to look like. So the idea is, if you want to train a really, really big foundation model, why not to train it on all this data and all this human understanding of the systems, and then use this tool, so to say, to fine-tune, apply, or whatever, to various different tasks in weather and climate related. Of course, this is a huge endeavor, and I mean, this was a small group, so we didn't scale up to full extent, but we got pretty far. But I'm not so much talking about the results or what is done here, but trying to get you a bit the intuition, or what really hyped me about this project. And that is that suddenly, if you want to train about all these different data sets and all these different modalities, and from all these different institutes, you encounter different variable names, you encounter different resolutions, you encounter different discretizations, you encounter different, even different simulation techniques, and so on and so forth. So you need to build a model which inputs all those, and basically lets the transformer magic, of course, work in this unified latent space representation. And that is, I think, the name of the game already in language modeling. Language is pretty easy because you can just encode a word as a vector, and then let's go. If you combine language with vision, it's a bit harder, because you suddenly need to get the vision data into the same, let's say, latent representation as language. This is done with CLIP and other models. And then there are other modalities coming there. So why not do the same here? And that's exactly what we did. And so you can think of an encoder which is versatile and takes all this different information to unified vector, which always has the same shape and always the same representation. And from there on, you can use the transformer. And this worked surprisingly well, to my surprise. I was maybe the only one surprised on this project how well it worked, but it influenced a bit my thinking. So I spent a year thinking of what to do with these new techniques, and when I've made up my mind, I want to go back to academia, I want to go back to Central Europe, basically industry. I was thinking a bit what is like the core of our industry, and this is very much about simulation data in all course of in all different areas, and we have many different simulation data. For example, on the lower right part, this is a classical CFD simulation in 2 dimension. We have this 4 obstacles and some turbulences forming. But there's also other data. For example, on the lower left, this is a classical dam break simulation. It's very hard to model because you have these free surface flows. So the wave is approximating this right border, and then it's breaking, so to say. And this is simulated with smooth particle hydrodynamics, and is one of these tough cases to check if your model works. On the upper left, you have a discrete element method. So these are methods which don't have any equations, which just follow interactions of particles, and therefore able to model microscopic phenomena. This is usually done in granular flows where you don't have so much information. And all of this data is somehow diverse, but somehow similar. And also, if you look at this discrete element method part, so at this green balls, if you want to describe it, you can describe it in one sentence. There's a bunch of grains moving up and down in a rotating drum, so it's super easy. But if you model the mathematics, it's actually pretty hard, because these are 1,000 particles. These systems go up to 1 million particles. So there is this discrepancy between mathematics, which is super hard, and like latent space dynamics, which look pretty simple. And this was really for me when I was thinking back of weather modeling, where we had this huge data, but we could all bring them to like compact latent representation. Why not use this similar tricks in all the simulations. And that's actually a work I'm doing. I'm trying to talk here about the idea because I think that this has many different directions to go forward. And we call it universal physics transformer. You have to always exaggerate a bit, so that's the name universal. But what that meant for me was we wanted to build a system which is able to take all this different data in first setup, because that's what we did for weather modeling, and this should work for other areas as well. So we wanted to build something which gets into a latent space which is always fixed, and that is pretty hard because you have different numbers of particles, you have either grids or particles, you have different simulations, and they all should come to a one fixed latent representation on which you can then use your transformers or whatever you use in your latent space to scale up. And this should scale because in the end, deep neural networks, they will have an advantage in these areas, but not in simulations with 1,000 particles, not on small 2D scales. There's no point in using neural networks there. Maybe it's like funny and you can do like some nice plots, but really to progress this industry or this area, you have to scale, because this is where numerical methods breaks down. You have to scale to millions of particles, you have to scale to large meshes, you have to go to 3D. So scalability is the big thing. And that means this fixed latent space is a good way of scaling, because if this latent space doesn't change, that means you can scale up the particles, because it's not going to explode computationally what you do in the latent space. So that is very important. And the way we do that is by having some sophisticated encoder. So this encoder is like a hierarchy where you select some of these nodes, some of these particles, which is, you see my mouse? Yeah, which is here. K is the number of nodes. So this is basically the nodes you select, and then you move all this information to these nodes, and then you apply some transformer layers which take this information and compress it to a fixed representation, which has the form n latent. So whatever number of nodes you choose, whatever grid you have, you basically can compress with a two-stage hierarchy to one representation. And then you run your transformer in this latent representation, and then finally you ask your network to query at specific points at the space. So this is the learning paradigm we visioned. Probably you can improve on that, but it has this properties that whatever you input, you get one representation. This representation is compact. That means you can scale, and you can run everything in the latent space. That means you are fast. I skipped that and just show some. I'm not so much about showing that we are better than others, because this is usually what deep learning papers are about, but more what I really like is, so this is the number of input points. So we train with different input points, but no matter what are the input points. If you go from 4,000 to 32,000, I think we went up to 256 in the end, but the performance is basically the same. So the network is trained to take all these points and basically take this continuous signal and work with it in the latent space, so it doesn't get distracted from this continuous signal. And this is the number of points, so the number of points we choose to propagate information, this first hierarchical layer, and also the more points you take for the trained model, the better it gets. That means it's also quite interesting, because you train with a fixed number of these points, but you can then use more points or less points. It still works. It's very versatile, and that is the direction we want to go. We did all this for grid-based methods because simply we didn't have the experience yet to scale to particle methods with over 1 million or even more particles. So we have to use grid sizes with large number of mesh cells. But of course we already starting to work on this simulation data, because this is where it gets really interesting, and this is where personally I'm most interested interested in, because I think deep learning will have a big impact here, because these SPH simulations, they take a long time. Discrete element methods, they have some problems. So this is where I expect to see some impacts. So this was really the first part I wanted to talk about. Do we get this data, how can we build these big models, what is important. For me, it's having a unified representation, being able to use multiple data, and being able to query different inputs and outputs. But you might ask the question now, what is happening if you don't have enough data? Because this happens a lot in engineering and physics problems. And this was the second thing I was constantly thinking. And this brings us back to PINs, so physics-informed neural networks, where I use the information of the PDE to basically train the neural network. 5 minutes? Okay. So a PDE is a boundary value problem. So it has initial, so it satisfies a equation with some boundary values. And what you're using is basically a neural network, which you force to satisfy this constraint optimization problem, and there you get the solution of the PDE from this problem. It's a very, very famous learning paradigm, and it's basically well used a lot already in engineering. But what we are asking, okay, if this works so well with PDE, why does it not work for geometry? Because you have similar things in geometry. Although you cannot write down the equations, you can write constraints, like it has to fulfill a design space, it has to plug in at some interface, it has to be connected, and so on and so forth. So you can really geometrically write down all these equations. So if we are able to write down these equations, theoretically we could train a neural network which fulfills this equation. This is done then completely without data, because usually in this geometric task you don't have a lot of data. And we can even go a step further, because these systems are underdetermined. So if we are able to make them like generative, then to make them output the worst solution, we're building something generative, because then we get different solutions. And that brings us to this paradigm where I will be very quick, because I'm running out of time. So that this way is asking 3 questions, which we try to answer as good as possible. There might be better answers to that. The first is, how do we represent these shapes? How do we enforce this constraint? And how we introduce diversity? So how to represent shapes? Luckily, as always, computer vision is helping, because neural fields are one of these standard tools. Yeah, it's working again. How we present audio, video, and other fields as a quantity of spatial and temporal coordinates. And that is a very, very good representation of such shapes as well. And what we are actually using is implicit shapes. So we are modeling these boundaries of this object. So everything within these boundaries is negative values. Everything outside of these boundaries has positive values, and exactly the boundary has the value 0. And these implicit neural shapes are very, very famous already in various different fields. What we want to do is we want to have a collection of shapes, because that's what I was saying. In the end, for different constraints, we want to have different outputs. So instead of just getting one output for one representation, we're asking the network to output several shapes. So this is the generative part. Okay, so neural fields to represent these functions, how to enforce these constraints. This is done by well looking a bit into geometry, and we start by writing sets of constraints. You can write them as for design region, so everything should be within this region, everything should be connected at different points, everything should be inside and not look outside. You have a mean curvature, everything should be smooth, and so on and so forth. You can really write down these things mathematically and come up with a loss function on that, which you then just combine as a unconstrained optimization problem, which you're minimizing. The hardest part for us was connectedness, because it's not so trivial to force shapes to be connected. We solved that with Moore's theory. I'm not going too much into that. It's very computational heavy. Hopefully we come up with something better. in the future, but it really made our shapes, so to say, work. I'm not, there is like many ways of how to introduce diversity. I will skip that because you intuitively can think of, if you have a set, you can always measure some dissimilarity of these different solutions, and if you enforce the similarity to be large as a loss, then you basically enforce the network to output different solutions. And this is what we are getting, so to say. So on the left, the losses we are optimizing are to be connected at discrete interfaces to have zero mean curvature. Then in the middle, we are optimizing that all these rays go through this point in the middle. And then on the right, we are optimizing interface, design region, and connectedness. The upper one is without connectedness, then of course it's not connected, and then if you enforce connectedness, this connects nicely above this obstacle. And we can get the generative part, so this is without the generative part, everything is, we see a nice mode collapse, and if we make it generative, then we get diverse solutions, and if we interpolate these solutions, of course, at some point they have to violate these constraints because the latent space is continuous. So we could go to 3D. We were already like trying to generate 3D shapes. This is of course far away from getting realistic topological optimization algorithm, but this is just an idea which I want to convey, which is right on the opposite of having this large data regime where you scale with data. Here you have this minimum regime of having basically zero data, but just constraints, and this is one of these two opposites in engineering, how we get further or get forward. And this already brings me to the last slide. So I tried to basically introduce or motivate why I think that large data area will be or is already hitting scientific research. It's about building foundation models. Foundation models is not so easy because foundation models means you need a lot of data, like literally by definition, and you need to enforce something like multimodality, which is not a priori clear what is it in physics or what is it in engineering. For me, it's this different simulation regime, like Eulerian and Lagrangian data, which I tried to show. And definitely we need to scale with the problems, because otherwise it's just no use in building these models. And then I tried in the second part to say, what is if we don't have data? What is if we just have constraints, as we have in a lot of problems? And I tried to show what happened, that you can write really down these constraints as it is done in physics-informed neural network and solve for that. Much more in underdetermined systems, you get some generative aspects. I have not touched any generative modeling. I've not talked about diffusion models in science, which are playing a big part, but I'm mentioning that as final remark. And that's, as I said in the beginning, I thank all my amazing people because they did most of the work. And thank you for having me.